You know, when you watch a master chef working during like a Friday night dinner rush, it looks almost like magic.
Oh, absolutely. It's a completely synchronized dance.
Right. They aren't just doing one thing at a time. They've got a reduction simmering on the back burner. They're perfectly searing a steak. And, they're simultaneously delegating the prep work for a complex salad.
Yeah, it's a beautifully synchronized web of tasks.
Exactly. But imagine if we forced that exact same master chef to work the way most of our current AI agents are built to work.
Oh boy, that would be a disaster.
Right. They would have to stand there just staring at a pot of water until it boils.
Just paralyzed until that one single task is done.
Yeah. Then cook the pasta, then plate the pasta, and only then would they be allowed to pick up a knife and start chopping an onion.
Huh.
The whole dinner service would completely collapse.
The inefficiency would be staggering. And, I mean, worse than just being slow, the chef would probably lose track of the broader context of the entire meal.
Because they're so hyper-focused on one linear step?
Exactly. By the time that sequential pasta was done, they'd have completely forgotten the exact temperature the steak was supposed to be cooked to.
Which brings us perfectly to why we are here today. Welcome to you, our resident learner, to another deep dive.
Glad to be here.
If you've been following the AI space, you know that AI systems that don't just chat but actually go out and take actions for you are basically the holy grail right now.
They are what everyone is trying to build.
But if you've actually tried to use them for complex, multi-step tasks, you've probably watched them stumble or loop or just completely forget what they were doing halfway through.
It is incredibly frustrating.
Today, we have the perfect shortcut to understand why that happens. We're diving into a brand new research paper that finally explains the problem, and more importantly, how to fix it.
Yeah, the paper is titled Atomic Task Graph, a unified framework for agentic planning and execution.
And our mission for this deep dive is to explore how this revolutionary framework is allowing small, lightweight AI models to completely outsmart massive proprietary giants like GPT-4.
It's a dense piece of research, but, well, it is fundamentally challenging the underlying architecture of how autonomous agents operate.
We're talking about a paradigm shift here.
Exactly. We're moving away from the assumption that if an AI fails at a complex task, it just needs a bigger brain, a bigger neural network.
Instead, it's about changing how it organizes its thoughts, shifting from a straight line to a web of interconnected tasks. Okay, let's unpack this.
Let's do it.
To understand why the Atomic Task Graph, or ATG, is such a breakthrough, we really have to isolate the bottleneck in current systems.
Right. And the researchers identify this bottleneck as the linear decision paradigm.
The linear decision paradigm.
Yes. The frameworks most developers use today to build agents methods you might have heard of, like React, which stands for reasoning and acting, or reflection, they're inherently linear.
So how does that actually work under the hood? Like, when a developer uses React to tell an AI to go book a flight in a hotel, how is the AI processing that structurally?
Well, mechanically, the language model is operating in a continuous loop of text generation.
Just generating one long string?
Basically, yeah. The AI is prompted to output a specific format. First, it writes out an observation, then a thought about that observation, and finally an action to take.
Okay, observation, thought, action.
Right. It executes the action, gets a result from an API or a web page, appends that result to the bottom of its text document, and then starts the loop all over again.
So the AI is literally building a massive chronological scroll of text containing every single thought, action, and piece of data it encounters along the way.
Exactly, a giant text document.
It's like playing the game of telephone, but combined with setting up a row of dominoes.
Oh, that's a good way to look at it.
Right, because if one domino falls wrong early on, the entire chain is doomed. And by the end, just like in telephone, the original message is completely distorted.
And that's exactly what happens. The scroll metaphor is highly accurate because of how LLM context windows work.
Because it has to read everything, right?
Yes. As that text history grows longer and longer, the model faces two distinct points of failure. The first is error propagation.
Ah, the falling domino.
Exactly. If the agent misinterprets a flight price on step 2, well, that incorrect thought is now permanently etched into the context window.
The error is just baked in.
It is. Every subsequent step it takes is built on top of that faulty textual foundation.
And because the AI relies heavily on the most recent text it generated, it just keeps compounding the mistake until the final output is, well, completely useless.
Right. If step 10 fails, the AI often just has to start all over from step 1. But the researchers point out a second, even more fatal flaw in this linear scroll:
Okay, what's that?
the explosion of hallucinated actions.
Hallucinations. Why does having a long text memory cause the AI to start making things up?
It comes down to attention mechanisms within the neural network itself.
Okay.
When you flood the context window with dozens of previous steps, some successful, some failed attempts, maybe huge blocks of HTML from a web search, the AI's attention gets completely diluted.
There's just too much noise.
The signal-to-noise ratio drops to near zero. The model gets overwhelmed by its own rambling history.
It basically confuses itself.
It does. It loses the thread of the original objective and starts hallucinating tools that don't exist or taking actions that just defy logic.
So if humans don't plan complex projects in a single unchangeable straight line, why do we force AI to do it?
If we connect this to the bigger picture, the paper is arguing that the problem isn't that our AI models aren't smart enough to book a flight.
Right.
The problem is that we are forcing them to do it using a data structure, a single, uneditable linear string of text that practically guarantees they will get confused.
And that prevents the AI from reusing verified intermediate results. Which brings us to the proposed solution, the atomic task graph, or ATG.
Yes, the ATG.
Since linear text chains are so fragile like that domino chain, the researchers completely discard them. Instead, they use a directed acyclic graph, or a DAG.
DAG, yes.
And they introduce this planning method called interface preserving recursive graph compilation.
I know, it's quite the academic mouthful.
It really is. So let's break down the mechanics. How does a text-predicting language model actually compile a graph? Because, an LLM just outputs words. It doesn't natively draw flowcharts.
Well, it does it through highly structured JSON outputs.
Okay, JSON code.
Right. Instead of prompting the LM to write a diary entry of its next thought and action, the ATG framework prompts the model to act as a system architect.
A system architect, I like that.
Given a complex user request, the LLM is instructed to generate a JSON object representing a graph network. This JSON defines individual nodes, which are the tasks, and the edges, which represent the data dependencies between those tasks.
Let's use this specific example from the paper to anchor this, because I think it helps.
Good idea.
The user prompt is, check tomorrow's weather in Beijing and provide travel advice.
Okay, so a traditional React agent would just instantly try to call a weather API.
And probably get stuck if it fails. But how does the ATG compilation process handle that same prompt?
The ATG compiler looks at that prompt and generates a high-level graph with 3 distinct nodes.
3 nodes. Okay, what's node 1?
Node 1 is weather retrieval.
Okay, grab the weather.
Node 2 is need determination, like analyzing the weather to see if the user needs an umbrella or maybe sunscreen.
Oh, that's smart. And node 3?
Node 3 is the final advice generation. But the architecture is recursive.
Meaning it goes deeper.
Right. The framework looks at node 1 weather retrieval and determines, well, it's still too vague.
It's too big of a task.
Yes. So it asks the LLM to break node 1 down into a smaller subgraph.
So it zooms in on that specific node and replaces it with, say, a node for identifying the correct API endpoint and another node for extracting the temperature integer from the raw API response.
Precisely. It recursively divides the problem until every single node is what they define as atomic.
Atomic, like indivisible.
Exactly. It represents a single direct tool use unit, like executing a Python script or hitting a specific search API.
Which brings up the interface preserving part of this massive academic title. That seems to be the absolute linchpin of the whole system. What does it mean to preserve the interface while it recursively builds this JSON graph?
Think of the interface as a strict contract of inputs and outputs for any given node.
A contract?
Right. If the high-level weather retrieval node requires Beijing and tomorrow as inputs and promises temperature and precipitation as outputs,
then any subgraph that replaces it has to honor that exact same contract.
Exactly. The external inputs and outputs must remain exactly the same. The framework strictly enforces this through schema validation.
And if it doesn't match?
If the LLM generates a subgraph that requires different inputs or outputs at different data type, the framework rejects the compilation.
Okay, I have to play devil's advocate here for a second.
Go for it.
That sounds like an enormous amount of bureaucratic overhead for the AI. You are forcing the LLM to constantly check input and output schemas, validate JSON formatting, recursively build trees. How does adding all this strict architectural overhead actually stop the hallucinations we talked about earlier? It just seems like giving the AI more things to get confused by.
It seems counterintuitive, I agree, until you look at what happens during execution.
Okay.
The massive payoff of these strictly defined atomic nodes is state isolation.
State isolation.
When the AI is executing the atomic node for, let's say, extract temperature integer, the framework dynamically restricts the context window.
Wait, it changes what the AI can see?
Yes, the LLM is only fed the specific historical context that is directly relevant to that specific atomic node.
Oh, wow. So it completely hides the 100-foot scroll.
It shreds the scroll. The model doesn't need to read the user's original request about travel advice, and it doesn't need to see the HTML from the umbrella research.
Because the inputs and outputs are guaranteed by the interface contract.
Exactly. The framework can safely blindfold the AI to everything except the immediate atomic task.
So the context window shrinks drastically.
It remains incredibly short and highly relevant. The signal-to-noise ratio is maximized, and the risk of hallucinated actions caused by a massive, rambling text history just drops off a cliff.
Okay, that makes perfect sense. The structure acts as a guardrail against the AI's own attention mechanism getting distracted.
That's a great way to put it.
But okay, we've successfully compiled this beautiful, perfectly compartmentalized JSON flowchart. But a JSON file doesn't actually do the work.
No, it doesn't.
The framework has to execute it. And this leads to the next major innovation in the paper, which they call dependency-aware execution. Because having a graph allows the AI to change the very nature of how it experiences time.
Right, the transition from planning to execution is where the graph structure truly outshines linear models.
Marvelous.
Because the JSON explicitly maps out the data dependencies. It literally states that node C requires the output of node B, but node D requires absolutely nothing to get started.
So the AI can instantly see which tasks don't depend on each other.
Yes. The execution engine performs what's called topological sorting. It instantly identifies tasks that are independent, which allows for independent branches to be executed in parallel.
So it can do multiple things at once.
It spins up multiple instances of the LLM to tackle independent branches simultaneously.
This brings us right back to our master chef analogy. The linear AI, the React model, is the bad chef. It waits for the chicken to finish roasting before it even starts chopping the salad.
It can only do one thing at a time.
But the ATG AI looks at the graph, realizes the salad has zero dependency on the chicken, and roasts the chicken and chops the salad at the same time.
It's bringing true, intelligent multitasking to AI agents. The efficiency gains are just huge.
Here's where it gets really interesting, though. Before it even starts cooking, the researchers implemented a pre-execution filter. They call it the thought experiment.
Oh, this is brilliant.
How does a text model simulate execution before actually interacting with the real world? Because, interacting with the real world is costly.
Well, it leverages those strict interface contracts again. During the thought experiment, the framework traverses the graph and performs internal type checking.
Checking the logic.
Yes. It looks at the output schema of node A and asks the LLM to simulate whether that output will successfully satisfy the required input schema of node B.
Without actually making any API calls.
Exactly. It does this without calling the weather API or executing any real code. It is purely checking the logical flow for missing steps, tool mismatches, or invalid dependencies.
It's basically checking for broken pipes before turning on the water.
That's exactly it.
And the data on this is wild. On the ALFWorld benchmark, which, for you listening, is a simulated environment for multi-step household tasks, they used the Mistral 7B model. Do you remember how many errors this internal simulation caught?
It caught 24.6% of risky plans before they ever went wrong in the environment.
That is massive. A quarter of the structural failures caught internally before they cost any compute time or API credits.
It acts as an incredibly cheap safety net. Instead of wandering down a doomed linear path for 20 steps before crashing, it catches it internally.
But, inevitably, even with a perfect plan and a thought experiment, real-world execution still goes wrong.
Always. Reality is messy.
APIs time out, websites change. The true test of an agent is how it recovers. Which brings us to ATG's most surgical feature, minimal necessary subgraph repair.
This repair mechanism directly addresses the fundamental fragility we talked about with the linear paradigm.
Where the agent scraps the whole plan and starts over.
Right. ATG solves this through state caching. Because execution is graph-based, every time an atomic node successfully completes its task, the framework freezes that specific validated region of the graph.
So the successful work isn't lost.
Exactly. It records the graph history in memory. So when a failure occurs, say an API endpoint throws an error, the agent doesn't panic.
What does it do instead?
It uses its recorded history to trace the failure upward. It searches for what they term the lowest common historical ancestor of the failed nodes.
So if we view the DAG as a family tree, it's walking backward up the branches until it finds the specific grandparent node where things diverge.
Yes, it finds the precise boundary of the error. Then it only repairs the tiny, affected subgraph.
Like replacing a bad tool or fixing a dependency?
Exactly. All the successful regions outside that boundary remain frozen and safe.
It's just like software engineering. It's like fixing a localized bug in one line of code instead of rewriting the entire operating system.
That's a perfect analogy.
But let me push back on this. Tracking the state of every node, tracing ancestors, recompiling subgraphs. Does this surgical repair actually save that much execution time in the real world compared to just starting over?
What's fascinating here is that the overhead is negligible compared to the time saved. And the hard numbers from the paper prove it.
Okay, hit me with the numbers.
On the ALFWorld benchmark, a standard React agent takes an average of 31.42 steps to finish a task.
31.42 steps.
Because it's constantly backtracking and repeating lost work. The ATG framework brings that down to just 18.36 steps.
Wow. 18.36. It fundamentally streamlines the AI's workload.
The local repair and the parallel execution combined mathematically mean the AI is doing significantly less busy work.
So we've seen the mechanics of the graph, the parallel execution, and the surgical repair. Now we really have to look at the scoreboard to see why this paper is making such massive waves in the AI community. The David versus Goliath benchmark takedown?
Yes, the benchmarks are where this gets undeniable. They tested this across ALFWorld for household tasks, WebShop for e-commerce, and ScienceWorld for scientific reasoning.
And the results are staggering. Let's look at Mistral 7B. When they upgraded it from linear React to the ATG framework, it improved by 49.16 points on ALFWorld.
A nearly 50-point leap just by changing the organizational structure.
And the hallucination rate. It plummeted from 42.86% under React down to just 12.14% under ATG.
Shrinking the context window works.
It really does. But the big reveal, the most shocking data point that brings it all home, is what happens with Llama 3.8b.
This is the real story here. Llama 3.8b is a very small open source model. It can run locally. It is tiny compared to the massive, proprietary, multi-trillion parameter giants.
But when ATG is applied to it,
When it's equipped with ATG, Llama 3.8b actually beats the massive proprietary GPT-4 running React on both ALFWorld and WebShop.
so what does this all mean?
It has profound implications for the industry. The prevailing narrative has been that we need to spend billions scaling up to larger and larger backbone models to get better reasoning.
Right, just throw more compute at it.
But this proves we don't necessarily need to do that. A smaller model with a superior organizational framework like ATG can completely outperform a giant model stumbling through a linear process.
Architectural efficiency over raw scale. And for you listening, this matters immensely for your life and work. As we rely more on AI agents to do our shopping, coding, and research, we need them to be reliable. We need them to be fast and capable of fixing your own mistakes without losing their minds in a text loop hallucination.
We want them to actually finish the job.
Exactly. ATG proves that working smarter, not harder, applies to AI just as much as it applies to us.
A solid organizational flowchart beats raw, unorganized brain power.
Which leaves us with a final, lingering, and frankly provocative thought to close on. Something not discussed in the paper, but impossible to ignore.
What's that?
If applying human-like organizational structures, delegation, parallel processing, localized repair, makes a small 8 billion parameter AI model this powerful, what happens when we eventually apply these exact same atomic task graphs to the massive multi-trillion parameter giants?
That is the trillion-dollar question.
Will they just organize our digital lives in the background, or will they become capable of orchestrating massive, real-world physical supply chains and human teams? It's something for you to mull over.
The ceiling for agent capability just got a whole lot higher.
It sure did. Keep questioning the structures behind the technology you use every day. Thanks for joining us on this deep dive.